This presentation is being provided with the support of Pierce County Amateur Radio Communication Service. ARCS is the 501c3 nonprofit organization that supports ARES operations within Pierce County and hosts internal and external communications for District 5 Pierce County ARES. As a nonprofit, ARCS relies on donations to provide these services. Please visit www.piercecountyarcs.net to see how you may contribute to ARCS. Thank you. Good evening, everyone. My name is Niles, N7SOI. I'd like to welcome you to the Near Vertical Incident Skywave presentation, which is part of the antenna series. We will be discussing the science involved, evolution, and methods for using NVIS to support the operational communications core capability. During an incident, one of our biggest challenges will be to maintain systems and processes that rely on infrastructure that may be unavailable or degraded. Many of our primary modes, such as WinLink, rely on communications infrastructure such as the internet, gateways, and digipeaters. Even voice communications can be significantly degraded if wide area coverage repeaters are degraded or lost. Near Vertical Incident Skywave, known as NVIS, is a means to reestablish those systems while infrastructure awaits repair or replacement. Here's the presentation agenda. Take a moment to review that. As I mentioned before, a disaster environment can have a major impact on our infrastructure and how we provide services to our served agencies. Our served agencies operate in the incident command system and rely heavily on the system's formal forms library. Furthermore, these forms must be complete, legible, and migrated into other systems such as Web EOC, while also being maintained by the documentation unit for later investigation and reimbursement. When systems and infrastructure begin to fail, NVIS propagation can provide a path to support formal and informal communications within the local area and regionally. NVIS propagation does not rely on repeaters or other infrastructure, but has a unique limitations that our operators should be aware of. High frequency NVIS propagation is an essential tool for operational communications during a large-scale disaster. Here are the abbreviations that will be used during the presentation. Please take a moment to review them. If you are following along with the PDF version of this presentation, you may want to refer to this slide later. Near Vertical Incident Skywave, known as NVIS, is a distinct method of propagation that allows for high-frequency radio communications at short to intermediate distances. NVIS fills the gap between direct line-of-sight paths and low-angle atmospheric reflection, which provide long-range communications. This method provides voice and digital communication at ranges of 30 to 400 miles, depending upon conditions. NVIS relies on the F layer of the ionosphere to reflect the signal back to Earth in a conical pattern around the transmitter. This method is particularly good at providing communications in areas where terrain masking precludes most other means. NVIS allows for high-angle wave penetration into valleys and depressions or to the other side of a mountain. However, NVIS communications rely on lower frequencies within the high-frequency band, generally 40 to 80 meter wavelengths. The usable frequencies are determined by the wavelength's ability to penetrate atmospheric layers. Frequencies below the lowest usable frequency will not reflect and be absorbed, while those frequencies above the maximum usable frequency will not reflect while penetrating the atmosphere. NVIS provides operators with very useful benefits that we all should consider adding to our stations and deployable resources. Predominantly, this propagation method allows the use of high-frequency communications at distances that may not be achievable with traditional skywave propagation. It allows for resumption of communications between nearby stations that do not have a line of sight when repeaters are lost, precluding the use of VHF or UHF bands. It allows communications in terrain that would preclude all bands without dedicated infrastructure and fills regional communications gaps with short to intermediate range voice and digital paths. However, NVIS is dependent on atmospheric conditions and a narrow range of frequencies between the lowest usable frequency, known as the LUF, and those below the critical frequency, known as the FOF2. Frequencies outside of this narrow band of spectrum will be absorbed or penetrate the atmosphere without being reflected as a usable signal. As we mentioned before, NVIS does have significant limitations. The reliance on atmospheric conditions to provide a narrow band of spectrum is the main limited factor. As the day progresses and conditions change, the permissible spectrum changes, which may preclude the use of static frequencies. Furthermore, the high takeoff angle must penetrate atmospheric layers before reflecting. Refraction in lower layers can cause signal degradation, noise, and minute frequency changes similar to the Doppler effect. These changes may also cause signals to become out of phase, which may cause negative multipath conditions. Station equipment may provide other limitations, such as the need for multiple antennas to provide NVIS or distant communications, which need lower angle signal propagation. NVIS antennas exhibit lower receive sensitivity and may require the use of a surface-laid reflector to mitigate marginal soil conditions. Lastly, NVIS antennas may require the use of wideband antenna tuners, balance, matching networks, or feed line chokes to allow their use or improve efficiency. The use of NVIS in the MCOM or OXCOM environment allows resumption of communications between isolated stations and may decrease the need for relaying traffic through multiple handlers. Each relay may be responsible for a 400% increase in message handling duty cycle. When we look at voice communications, the average duty cycle for a voice message is greater than 5 minutes. Each relay would double the time, increase the margin of error, and make chain of custody much more difficult to maintain. NVIS allows for direct communication, bypassing many of those drawbacks. Furthermore, Pierce County may become geographically isolated from state government during a major disaster. The Cascade Mountain Range provides a natural barrier to communications between eastern and western Washington. Without infrastructure, communications may be lost with state agencies as they reestablish operations outside of the affected area while exercising their continuity of operations plans. NVIS propagation may be a method to reestablish communications with these agencies once they relocate to gain access to distant gateways that still have functioning internet. This ability to fill communications gaps is leading many amateurs and agencies to explore NVIS communications and to dedicate resources to build NVIS capacity. Let's go ahead and hold here real quick. Does anybody have any questions? Hearing none, we'll move on to the historical usage. NVIS technology has been in use for nearly 100 years. During World War II, the German Wehrmacht developed and refined its use to facilitate their Blitzkrieg or lightning war strategies that relied on fast-paced, coordinated, motorized, and mechanized penetration of defensive positions. These penetrations often exceeded the capabilities of their existing communications equipment. Once a forward unit lost contact with their operational strategic level command, they were exposed and at significantly greater risk. NVIS propagation allowed them to conduct these operations and account for much of their success on the Eastern Front, where individual battles may extend across vast distances. NVIS was adopted by the United States later in the war and was used to coordinate communications on D-Day between landing forces in France and operational and strategic leadership in England. The US military exploited the technology to a greater extent during the Vietnam War, where the country's topography precluded low-angle propagation. Without NVIS communications, many large-scale heliborne operations would have been impossible. With the emergence of newer technology, FM communications increased in the military. As the military shifted to a reliance on low-band VHF FM communications, far less time was spent on HF communications. At the tactical level, HF communications became almost non-existent. HF communications became relegated to operational and strategic levels to provide backhaul communications. Desert Storm offered the United States an opportunity to exercise large motorized and mechanized formations for the first time since World War II. The environment facilitated fast-paced operations similar to the Germans' Blitzkrieg. And once again, intermediate range communications became a limiting factor. The experience in Desert Storm spawned greater interest in satellite communications, mainly global positioning systems and satellite communications. Both technologies offered leadership reliable communications and greater coordination of ground forces than was previously possible. This mindset would extend throughout most of the global war on terrorism. However, as reliance on satellite technologies exploded, the cost and reliability of these platforms dramatically increased. Most of these systems relied on contracted satellites, which are not secure. As we're moving into an era of near-peer threats, the United States military is once again re-evolving their communications technology to provide secure communications in an environment that may disrupt or destroy satellite communication resources. This graphic depicts the evolution of NVIS technology used by the military, which provides the basis for amateur radio NVIS propagation. As we mentioned before, the German Wehrmacht encountered communications gaps in the intermediate range. They developed NVIS technology, including antennas and techniques. The photos on the right side of the screen show German half-track command vehicles employing NVIS antennas above the crew's head. While it may appear that these vehicles have a roll cage, they are actually NVIS antennas. The second picture is of General Oberst or Colonel General Heinz Guderian operating from his command vehicle in France following D-Day. Guderian was one of the principal developers of the German Blitzkrieg strategy and employed NVIS communications to organize the German defense of France during the Allied invasion to reclaim Europe. At the same time, Allied forces were using NVIS to communicate with operational and strategic level commands in England. The US utilized NVIS during the Vietnam War before becoming reliant on short-range FM communications. During the post-Desert Storm era, the military relied heavily on satellite-based technologies. As distances expanded in Iraq and Afghanistan, some elements revolved back to NVIS communications, which led to the fielding of greater amounts of HF communications equipment among tactical forces. With the reemergence of near-peer threats, HF communications and NVIS have once again gained in popularity and are becoming increasingly utilized to avoid satellite-based communication systems. Let's hold here. Do we have any questions? Okay. Antennas may provide different forms of propagation, depending on a variety of factors, including the band, antenna orientation, and topography. Ground waves account for most radio communications. There are three types of ground waves: direct, reflected, and surface. Ground waves are susceptible to reflection, refraction, and diffraction, depending on the band. While direct waves require line of sight, the band and conditions may allow reliable communications even when an obstruction occurs. Ground reflected waves may reflect off the ground surface or another surface to establish a viable signal. Surface waves may refract along the Earth's surface. Surface waves are affected by the Earth's electrical characteristics, which cause the signal to follow topography rather than reflect off of a surface or diffract around obstructions. In this graphic, we're reviewing direct wave propagation. Direct waves are primarily line of sight, but may experience refraction and diffraction. To improve direct wave propagation, You may increase antenna height or relocate the antenna to a location with better line of sight between the stations. Ground reflective waves function in a similar method to atmospheric skywave propagation and rely on the signal to be reflected off of a surface to establish a signal path. However, reflected waves may be out of phase with direct waves and cause multipath condition. This phenomenon may result in loss of signal resulting from the out of phase signals canceling each other out at the receiving station. Surface waves are refracted along the Earth's curvature, resulting from the Earth's electrical conductivity and dielectric constant. An example of this may be found in VHF bands, which tend to refract into depressions where UHF signals do not. VHF also exhibits greater diffraction around obstructions such as buildings, while UHF exhibits better penetration of buildings. The three types of ground waves are limited to short-range communications and are susceptible to obstructions. For long-range communications, skywave propagation is required. Skywave propagation relies on the atmosphere to reflect and refract radio waves, generally at low angles, to allow long-range communications. The lower the angle of incidence or takeoff angle, the greater the distance the radio wave will travel. The takeoff angle and reflection causes an area between ground waves and sky waves to be skipped by a viable signal. This is known as the sky zone. The greater the skip distance, the greater the sky zone will be. Reliable communications cannot be achieved in the sky zone at low takeoff angles. NVIS fills this gap using a high angle of incidence at frequencies below the critical frequency. Higher frequencies will penetrate the atmosphere unobstructed. We'll hold here for questions. Hearing none. Earth's ionosphere provides the reflective surface to achieve skywave propagation. There are 3 to 4 layers depending on the time of day. These layers are the D, E, F1, and F2 layers, with the F2 only occurring during the day. The F layer or layers provides frequencies below the critical frequency, a varying level of reflectivity based on the time of day, solar weather, and other atmospheric conditions. Frequencies below the lowest usable frequencies will be attenuated and refracted by the D layer. The D layer also attenuates and refracts signals above the lowest usable frequency, but does not preclude their use. Ionization of the atmosphere determines the density and reflectivity of the F layer. Some communications may also be achieved using the E layer. These are some key terms when discussing skywave propagation. Frequencies above the critical frequency will penetrate the atmosphere without being reflected. The maximum usable frequency is used to determine the highest frequency that may be used for low takeoff angle long-range communications. Atmospheric attenuation and diffraction in the D layer determines the lowest usable frequency that has a high enough signal to noise ratio to achieve viable communications. Lastly, the frequency of optimum transmission describes a notional frequency which may provide the best results along a given path based on mathematical computation rather than a propagation sounding. The critical frequency, maximum usable frequency, and lowest usable frequency are determined by atmospheric soundings conducted by atmospheric and space weather agencies. While most skywave propagation is oriented to achieve low takeoff angles to maximize long-range communication, NVIS relies on high takeoff angles to achieve a near vertical angle of incidence to produce a conical reflection pattern. The conical reflection pattern provides near continuous coverage without a skip zone. However, ground wave propagation may also be received out of phase at the receiving station, which would null the signal. For planning purposes, it is estimated that this phenomenon may extend to 30 miles, which would appear as a skip zone. When using NVIS, the critical frequency is paramount. There are online resources to assist in determining the critical frequency, as well as software that will assist an operator in determining their frequency choice. As planning figures, 40 meters is used during the day and 80 meters at night. However, depending on atmospheric conditions, 60 or 80 meters may be used during the day and potentially 160 meters at night. As we just mentioned, frequency selection will depend on conditions. Under some conditions, frequency as high as 30 meters or as low as 160 meters may be used. It is recommended that operators become familiar with the online tools to predict atmospheric conditions to guide frequency selection. A quick note, due to the conical reflection pattern, NVIS signals are difficult to direction find. This is another reason that the military has used NVIS propagation for almost 80 years. NVIS antennas must be horizontally polarized and located within 1/20th to 1/4 of a wavelength above ground. The optimum height is about a quarter wave. However, ground height can be misleading. Some soil conditions may be permeable to radio waves, which will cause the antenna to perform as though it was mounted much higher above ground. The proximity of the ground provides a reflective surface for the radio waves to be directed straight up. In the case of poor soil conditions, a reflector between 10 to 15% longer than the radiating elements may be necessary beneath the antenna system. Some operators choose to use multiple reflectors to increase efficiency of the reflected waves and focus more energy into the vertical pattern. Any questions before we move on?
I just have one comment, Niles.
Go ahead.
And that is, those of us that use NVIS antennas, we've even seen the difference between this last summer, very, very dry, and our normal Washington ground lines. Usually it's wet enough around here that most of us don't have to add an additional ground beneath the antenna. But here this summer, to get the same kind of coverage, we had to do that. So it's always changing.
Absolutely. Any other questions or comments before we move on? This is a picture of how the critical frequency is depicted in many of the online resources. This graphic was collected in the midst of a solar minimum, and the critical frequency for North America failed to exceed 60 meters during the day. 80 meters would have been the best choice based on this sounding. Let's hold for questions on this one, because many of you may never have seen one of these diagrams before or have potential questions. So I will hold for questions. Hearing none, we'll move on. This graphic shows another way to view the critical frequency, but I prefer the other graphic. This is less intuitive for most users. Unless you're a statistician and you like looking at graphs, a visual picture provides a better intuitive grasp of the information. In this graphic, we can determine the maximum usable frequency. When viewing this graphic, apply how you would use a topographical map and treat each line as a contour line. Only in this case, they display frequencies rather than elevation. According to this graphic, our maximum usable frequency would have been lower than 10 to 13 megahertz. NVIS antennas come in many forms. They must be horizontally polarized and located less than a quarter of a wavelength to the ground. Within that guidance, there's a lot of room for experimentation antenna types. The most common is a low-mounted dipole or folded dipole, which may be oriented horizontally or in an inverted V. The AS2259 is based on a dual band 40 and 80 meter inverted V antenna at right angles to provide the guy lines. Other styles are full wave loops, slinky antennas, hamstick dipoles, long wires, and vertical whips angled parallel to the ground. The picture on the right is an AS2259 style antenna with a dual band VHF and UHF vertical antenna mounted above the feed point. I found this style to be an easy to make antenna system that can support all band, all mode radios to be a fully functioning station while deployed. The second picture is a low mounted folded dipole with a reflector placed beneath the radiator. Sand can provide poor soil conditions for NVIS antennas due to the lack of moisture. Using a reflector is often necessary in a desert environment. And as Stan mentioned, we suffer from the same thing if our conditions change and the amount of moisture in the soil decreases. So it's not just a desert, but you will experience it in a desert. Any further comments before I move on?
Comment.
Go ahead.
That AS2259, if you take the strict military lines for that, that's not cut to ham frequencies. But there is a website that shows you how to make the coils to stick in there to make it exactly on the ham frequencies. And that's what I've put up, and it works quite well as a third antenna for the 60 meter.
Yep, absolutely, John. And part of that reason the lengths are off aren't just the frequencies, but they actually use the antenna mast as the feed line, and it kind of changes the characteristics as far as common mode current. So yeah, if you're interested in building an AS2259, I'll show some links a little bit later on, but it does wait one, but it will change the lengths. I prefer to actually leave the lengths long and use a winder to shorten or lengthen them based on the frequency that I'm using. And John's also absolutely correct. You can add a third dipole for 60 meters, or you could even add one for 160 meters if you really elected to do so. Go ahead with your comment, Doug.
Yeah, I believe the territory involved for that is quite large, about 85 feet on a square grid. There is another one that's an L shape from the top plan that's 38 feet, and it's an L shaped, and Mark Yordi has shown this, and you may later on, that works effectively on both 80 and 40. I haven't tried it on 60, but it works well on both of those bands. Back to Dent.
Yep, another option is to use coils like John mentioned and what's shown in the picture for the 80 meter. I prefer to use the coils, and that way it's a square footprint as opposed to having a shorter leg and a longer leg, and decrease the amount of real estate that you need. The inverted L also is another technique, and we're going to show some that even take up a smaller footprint.
Right, mine was I fit it in my backyard.
Absolutely. Just about any type of dipole may be used to erect an NVIS antenna. The hamstick dipole offers operators a very easy to deploy NVIS antenna system for Go kits. If you choose to build this style, you may want to add a reflector 10 to 15% longer than the radiators of your kit. Hamstick dipole is probably about the simplest and easiest and fastest antenna that you can put up for NVIS. Because you don't need something to support the various legs of an inverted V or an inverted L. It can be put on a fiberglass tripod between 16 and 18 feet tall, and you're in business. HF whips are folded into a horizontal configuration will also work. Even while mobile, they'll still continue to work without a reflector. In a static location, a reflector is advised. In-fed antennas and other dipoles will also work. There are many commercial options available. If you want to purchase commercial off the shelf, I will say that not all providers have the same quality control. Do your research before buying commercial off the shelf equipment. Also be careful when a manufacturer says they are used by the military. They may not have been provided by the military and purchased by an individual. When reviewing similar antennas, one manufacturer states they are used by the military, but are made from poor quality PVC components. Their competitor uses quality materials and has a much higher quality control, but costs more. I won't name any names, but I did not include a picture of that competing company. A few years ago, I was asked to visit the 7th Infantry Division headquarters on JBLM. First Corps commander had directed the satellite communications links would no longer be used, and for division and below commands to migrate to HF communications. The brigade was in the field and could not establish communications with the division headquarters. After speaking to them on the phone, I explained to them the difference between ground wave, skywave, and NVIS. I gave them some rough instructions to fold their vertical antenna over and use a reflector beneath it. They were able to establish communications with the deployed brigade. This is a picture of that setup when I viewed it the next day. As you can see, they're using their comms vehicle. The vertical antenna is a VHF low band antenna, and their NVIS antenna is folded over. They used a extension cord as their reflector underneath that antenna, and they moved their feed point from directly beneath the antenna base to a tuner that was located on the ground, and their Harris representative told them to cut an extension cord and splice the extension cord between the auto tuner and the feed point of the antenna. As you can see in the picture, that extension cord is laying on the ground and the full length of the extension cord is radiating. So they were able to establish communications, and I'm sure that antenna tuner thought it was an excellent match. The antenna tuner was connected to the radio by 75 ohm coax that was purchased from Home Depot. So as I mentioned, the military has become very afraid of HF communications, and they are relearning all of these lessons. And their focus is at NVIS to provide communications between tactical and operational elements. So they're still trying to figure it out, even though they should be the subject matter experts. Here are some commercial off-the-shelf NVIS mobile antennas. Each costs many thousands of dollars and have tuners and other built-in equipment. You could achieve similar results with an auto tuner and a horizontally oriented vertical whip. You could also use a hamstick dipole. I would advise you to consider the RF energy you may be transmitting and perform an RF safety inspection. Here are the key points. Horizontal polarization, mounted low to the ground. About 18 feet is great. Consider a reflector for poor ground reflection. You may need a balun or matching network to account for low impedance at the feed point. NVIS antennas have high common mode current. Consider a feed line choke or the aforementioned balun. Plan for a wider band tuner than your built-in tuner. Frequencies may need to change based on conditions. Monitoring space weather can be very beneficial. Hopefully you'll consider an NVIS addition to your station or deployable resources. They can be cheap to make, or you may already have everything you need to build one. Here are some online resources to help you research a potential path forward. Many ARES members have experience with NVIS or building the antennas necessary. Please feel free to reach out to your team leadership, a mentor, or myself. I hope you've enjoyed this presentation, and thank you all for attending. This concludes the formal portion of the presentation, and we thank you for your patience and attention. Does anyone have any questions related to the course content? Please hold all other questions and comments until after the recording has been terminated. Does anybody have any questions, comments? Need me to go back to a particular slide? Hearing none. Again, we'd like to thank everyone for participating and hope you enjoyed the material. Once again, this presentation is being provided with the support of Pierce County Amateur Radio Communications Service. ARCS is the 501c3 nonprofit organization that supports areas operations within Pierce County and hosts internal and external communications, including our website and social media presence for District 5 Pierce County areas. ARCS also manages property and provides communications resources within Pierce County, such as repeaters and Go Kits. As a nonprofit, ARCS relies on donations to provide these services. Please visit www.piercecountyarcs.net to see how you may contribute to ARCS. Thank you.